the real reason Mars turned from a living world into a dead planet. Tonight, I want to tell you about two planets. 4 billion years ago, Earth and Mars were both warm, both wet, both quietly waiting for something to happen on their surfaces. Then, on one of them, life began. On the other, the engine went quiet. In this video, we will walk through what that engine was and why a planet only gets to keep it if it is born big enough. By the end of tonight, you will understand the real reason Mars is dead and Earth is not. So get yourself comfortable. Pull a blanket over you. Make whatever warm drink helps you settle. And let the lights go low. Let your shoulders drop. Let the room go quiet. We're going to take our time with this one. Now, let's begin. Take a moment and picture Mars in your head. Just the basic image. Rust-colored, dry, cold. The planet you have seen in every textbook, in every photograph from NASA, in every science fiction movie. A red rocky desert with thin air and nothing alive on it. That picture is correct. It is the Mars of right now. The Mars sitting in our sky, 400 million kilometers away. The Mars that humanity has been visiting with robots since the 1970s. That is what Mars looks like today. But before I go further, I want to be honest with you about one phrase in tonight's title. The title says Mars used to be a living world. When I say that, I do not mean we have proven that life ever existed on Mars. We have not. No fossils, no microbes, no confirmed biology. Nothing in the data today definitively proves that anything was alive on Mars at any point in its history. What I do mean is that Mars used to be the kind of world where life could have lived. There's a difference between those two ideas, and the difference matters. A living world, in the way I am using the phrase tonight, means a world with the conditions for life. Liquid water, a thick enough atmosphere, a protected surface, time. Mars had all of those things, billions of years ago. Whether it ever used those conditions, whether anything actually grew or swam or breathed in that ancient environment, is a question we still cannot answer. Now, with that honesty in place, let me show you the second picture of Mars. The picture that almost nobody carries in their head. The picture from 4 billion years ago. 4 billion years ago, Mars was warm. Not Earth warm, but warm enough that water on its surface could be liquid. Not Earth wet, but wet enough that rivers flowed across its land. There were lakes. There were river deltas. The northern hemisphere may have held a shallow ocean, covering about a third of the planet's surface. The atmosphere was thicker. The sky may have been blue or pale yellow, not the dim orange we see today. Clouds drifted across red rock. Rain may have fallen. Snow definitely fell. The water cycle, the same kind of cycle Earth still has, was running on Mars. And the timing is the part that I find most quietly devastating. 4 billion years ago is exactly the same window when life was first beginning on Earth. The same patch of solar system history. The same kind of conditions. The same chemistry. Two planets, almost the same age, sitting in nearly the same neighborhood around the same young sun. Both with rivers, both with skies, both with the slow patience that life needs to start. On one of those planets, something began. On the other one, nothing did, or whatever began was lost. And then Mars started to change. Slowly at first, then less slowly. Across hundreds of millions of years, the world we picture in our heads today, the cold red desert, replaced the world that used to exist there. Not overnight, not in a catastrophe, in a long, patient erasure. Tonight, we're going to walk through that erasure. We're going to look at what made Mars warm. We're going to look at what took the warmth away. And we're going to end at the one real reason behind all of it. Because the loss of water, the thinning of the atmosphere, the freezing of the surface, are all consequences. There's a deeper cause underneath them. And the deeper cause is the one that makes the whole story make sense. Mars did not just lose its water. It lost the ability to keep its water. And that ability is something a planet only gets if it is born big enough to hold it. Hold that line in your head. We will come back to it. To understand what happened to Mars, you have to understand when it happened. So let me give you a very simple timeline. Mars formed about 4.5 billion years ago, around the same time as Earth, from the same disk of dust and gas around the young sun. The early Mars was hot, molten, with a lot of internal heat from its formation. As it cooled, a crust formed. Volcanoes pushed gas out. Water condensed. The atmosphere thickened. By about 4.1 billion years ago, Mars had a real environment. Rocks, water, sky, weather. The period that followed, lasting from about 4.1 billion years ago to about 3.7 billion years ago, is called the Noachian. The name comes from a region of Mars called Noachian, which preserves rocks and landforms from that era. The Noachian is the period when Mars was at its most Earth-like, when the planet was warm enough, wet enough, and protected enough that the surface looked, by some measures, more like our world than like the modern Mars. 400 million years is a long stretch of time. To put it in human scale, 400 million years ago on Earth, the first plants were just colonizing dry land. Fish were starting to crawl out of water. The very early steps of complex life were happening. Mars had as much time, possibly more, in its warm, wet phase as Earth had between the first land plants and now. That is the strange thing to hold in your head. The window for life on Mars was not short. It was not a flash. It was a sustained, multi-hundred-million-year window during which the planet had liquid water on its surface, a thicker atmosphere, and stable conditions. Whatever was going to start on Mars had a long time to start, and we have evidence, real evidence, of what the surface looked like during this period. Not guesses, not speculation, actual landforms preserved in the Martian rock that match exactly what flowing water leaves behind on Earth. A 2025 study from the University of Colorado Boulder, led by a researcher named Brian Hynek, mapped over 15,000 kilometers of ancient riverbeds in the Noachian region. 15,000 kilometers. That is roughly the distance from one side of Earth to the other. A network of rivers, branching like trees, carving valleys into the highlands, all preserved in Martian rock from the Noachian era. That much river is not the kind of thing a planet has by accident. That much river requires sustained rainfall, or at least sustained snowmelt, over a long period. The water did not just appear briefly and vanish. It flowed. It eroded. It deposited sediments. It did all the things rivers do on Earth, except it did them on the surface of a planet that today has not had a single liquid surface river in 3.5 billion years. So the Noachian is not a hypothesis. It is a measurable, mappable, well-documented chapter in Martian history. Mars had rivers. We can see them. They are still there, in dry preserved form, waiting for us to read them. Let me take you to one specific place on Mars. A crater. A particular crater that, if you have followed any space news in the last 5 years, you have probably heard of. The crater is called Jezero. It sits in the northern hemisphere of Mars, just north of the planet's equator. It is about 45 kilometers wide, roughly the size of a small American county. From orbit, it looks like a circular bowl carved into the red highlands. Nothing dramatic, nothing obviously special. But when scientists at NASA looked at Jezero from orbit, they saw something extraordinary. On the western edge of the crater, where a small valley enters from the highlands, there was a fan-shaped deposit of sediment. The shape was unmistakable. It was a delta, the same kind of delta a river makes when it flows into a lake on Earth, dropping its sediment as the water slows and spreads. On Earth, the Mississippi River makes a delta where it meets the Gulf of Mexico. The Nile makes a delta where it meets the Mediterranean. Every major river on Earth that empties into still water leaves the same fingerprint, a wide, branching, flat deposit of mud and sand and rock, building outward over time as the water dumps what it was carrying. Jezero has that fingerprint. From orbit, visible, 45 kilometers wide, with a delta on the western edge, with sedimentary layers preserved in the rock around it. The conclusion was obvious. Jezero used to be a lake, a real one, with a river flowing into it, with water sitting in it long enough for sediments to settle and layer and harden into stone. In February of 2021, a NASA rover called Perseverance landed inside Jezero crater. It has been there for nearly 5 years now, and what Perseverance has found on the ground has confirmed everything the orbital images suggested. Sandstone, deposited by flowing water. Boulders, the kind that only get carried by deep-moving rivers. Clay minerals, the kind that only form when rock spends a long time soaking in water. Layered sediments, exactly the kind of pattern a lake floor preserves over centuries of slow accumulation. Then, in 2026, Perseverance found something even more remarkable. Using a ground-penetrating radar instrument called RIMFAX, the rover looked beneath the surface of Jezero. The radar detected an older buried water-shaped layer beneath the surface, sitting tens of meters below the lake floor we already knew about. The interpretation suggests a previous episode of water activity at Jezero, before the lake we currently see at the surface was even formed. Whatever the exact details, the picture is the same. Water at Jezero was not a brief incident. It was a recurring fixture of the landscape, lasting longer than anyone had originally guessed. And Jezero is not unique. The Curiosity rover, in a different crater called Gale, has been exploring another ancient lake bed since 2012. The same kind of sedimentary layers, the same kind of water-altered minerals, the same kind of preservation. Two rovers in two different craters, separated by thousands of kilometers, are sitting on lake floors that are roughly the same age. This is what we mean when we say Mars used to be wet. We do not just mean the orbital images suggest something. We mean two robots are physically standing on dried lake floors, drilling into the rock, finding the chemical signatures of long-vanished water, sending the data back to us across hundreds of millions of kilometers of empty space. Mars had lakes, and the lakes were stable, and whatever was going to start in those lakes had time. I want you to picture the early solar system. Specifically, 4 billion years ago, around the young sun, the inner planets are settling into their orbits. Mercury is the closest, baking under direct heat. Venus is the second, with its early atmosphere starting to thicken. Earth is third, slightly larger than Venus, with shallow oceans forming on its surface. Mars is fourth, smaller than Earth, sitting where the orbit is colder, but where the planet still has enough sunlight to keep things warm with a thick enough atmosphere. And here's the part that surprises most people. 4 billion years ago, Earth and Mars were not as different as they look today. They were both rocky planets. They both had atmospheres. They both had liquid water on their surfaces. They were both, in the rough sense of the word, habitable. If you had been there, looking at both planets at once, you might have thought Mars had an even better chance. Earth was being hammered by enormous impacts during this period, the late stages of what astronomers call the late heavy bombardment. The moon was closer to Earth, raising tides hundreds of meters tall. Earth was a rougher, more violent world than the textbook pictures suggest. Mars, smaller and less massive, was actually calmer in some ways. Its surface had less impact violence proportionally. Its atmosphere was thicker than today's, by orders of magnitude. The conditions on Mars during the Noachian were genuinely competitive with the conditions on Earth during the same window. And that window, 4 billion years ago, is exactly when life on Earth was beginning. We do not know the exact date. We may never know. But the chemical evidence, the fossil microbes preserved in some of Earth's oldest rocks, the carbon isotope ratios in ancient stones, all suggest that something biological was happening on Earth somewhere between 4.1 and 3.7 billion years ago, right in the middle of the same window when Mars had its own warm, wet phase. So the question is not whether life could have started on Mars. The question is whether it did. And we do not know. But the conditions were there. The window was there. The same chemistry that worked here had a chance to work there. Now stand back from the picture for a moment. Two planets, both warm, both wet, both with skies and weather and water cycles, both with the slow patience that life seems to need. And then, over the next several 100 million years, the picture changes. Earth keeps its conditions. Mars loses them. The reason for that difference is what tonight's video is about. Why one of these two planets stayed warm and wet, and the other one became the cold red desert. The answer is not luck. The answer is not random catastrophe. The answer is built into the planets themselves, into the size and structure of the bodies, into the deep machinery that we are about to walk through. Mars did not lose its conditions because something hit it. Mars lost its conditions because of what Mars was made of, and how big it was, and what those facts together meant for the planet's long-term ability to hold on to what it had. To see why, we have to go inside the planet. We have to look at the engine. Before we go inside the planet, I want to show you what the next few billion years looked like, on the surface, in slow motion, because the science we are about to walk through is mechanical, but the picture it produces is deeply cinematic. And the picture is worth holding in your head as we move through the mechanisms. Picture Mars 4 billion years ago. Stand on the rim of a high crater in the highlands. Look out across the landscape. Below you, in a low basin, there is water. Not blue like Earth's oceans, but blue-gray under a paler sky. River channels cut across the red rock between the highlands and the basin, feeding the water. There are clouds overhead, thin but real, drifting in the same slow curls Earth's clouds make. The atmosphere is thicker than today's by far. You could probably breathe, if you held your breath, for short stretches. The temperature on a warm day might be just above freezing. Water on the ground stays liquid in the daylight. At night it freezes, but in the morning it melts again. The cycle holds. This is the Noachian Mars. The Mars where, if anything was going to start, it had its window. Now run the clock forward. Slowly, across hundreds of millions of years, the sky thins. Not dramatically at first, just slightly. The pressure drops. The thicker air becomes thinner air. The cloud cover decreases. The sunlight reaching the surface becomes more direct, less filtered. The protective shield around the planet, which was already weaker than Earth's, weakens further. The solar wind, the constant breath of charged particles from the sun, starts to reach deeper into the upper atmosphere than before. The atmosphere slowly gets eaten from above. Year after year, million after million, as the air thins, the temperature drops. With less atmosphere to trap heat, the surface gets colder. Liquid water becomes harder to keep liquid. The lakes start to freeze in winter and not fully melt in summer. The river systems run less consistently. Some of them dry up. Some of them get covered in dust. The water cycle, which used to run continuously, becomes intermittent, then rare, then gone. By the time 3 billion years have passed since the warm wet phase, the surface of Mars is cold. The pressure is so low that liquid water cannot exist on the surface for any significant time. Any water that is exposed to the air either freezes or evaporates almost immediately. The rivers are dry beds, preserved in the rock. The lakes are flat plains of dust. The Northern Ocean, if it existed, is gone, with its water either lost to space or frozen into the ground or trapped deep in the crust. And the sun is still there, the same sun that has been there the whole time, sandblasting the surface with radiation that, on Earth, the atmosphere and the magnetic field absorb almost completely. On Mars, that radiation reaches the ground. It breaks apart organic molecules. It oxidizes the soil. It turns the surface into a chemical environment that is hostile to anything biological. By the time we're looking at Mars today, the transformation is complete. The cold red desert, the thin air, the freezing dust storms, the radiation-soaked surface, the same planet that, 4 billion years ago, had rivers carving into rock under a thicker sky. The change did not happen because something hit Mars. It happened because something inside Mars stopped working. The deep machinery that protected the warm, wet phase quietly went silent. And once the machinery was silent, everything else followed in a chain that took the next several billion years to complete. We are watching the last frame of that chain today, when we look at Mars in our telescopes. So the question becomes, what was the machinery, and why did it stop? That is where we are going next. And before we go on, if you are still with me and you are enjoying tonight's walk, take a moment to subscribe, so this kind of slow, careful science can find more curious minds. It costs you nothing, and it helps these videos reach the people who would actually love them. A small thing for you, a real thing for me. Thank you for being here. Every rocky planet, when it forms, is hot. The energy of formation, the kinetic energy of all the dust and rocks crashing together to build the planet, gets converted into heat. By the time a planet has fully formed, the inside is molten. Iron and nickel, the heaviest common elements, sink to the center. The lighter rock floats on top. The planet ends up with a layered structure. A solid crust on the outside. A thick layer of hot rock underneath, called the mantle. And at the center, a core made of metal. The core is the engine. Let me show you what I mean. Find a magnet, the kind you stick on a fridge. Sprinkle some iron filings on a sheet of paper. Hold the magnet underneath. The filings line up in curved lines, going from one end of the magnet to the other. From the North Pole, around through the air, and back into the South Pole. Those curved lines are the magnetic field. The magnet has a force around it. The force is invisible, but the iron filings make it visible. Now scale that picture up to the size of a planet. The metal core inside Earth is mostly iron and nickel. It is incredibly hot, around 5,000 degrees Celsius at the very center. The outer layer of the core is liquid metal. The inner layer is solid. And here is the key fact. The liquid metal in the outer core is constantly moving. It churns. It rises and falls. It flows in slow patterns across the depth of the core, like very hot, very heavy weather happening hundreds of kilometers below the surface. That motion of liquid metal generates electricity, and the electricity, in turn, generates a magnetic field. The same kind of field as the fridge magnet, but planet-sized. The lines come out of the North Pole, curve all the way around the planet through space, and dive back into the South Pole. This whole process, where a moving liquid metal core generates a magnetic field around the planet, is called a dynamo. The word comes from the same root as dynamic, meaning movement. A planetary dynamo is literally the planet generating its own magnetism through the slow motion of its own deep metal. Earth has a dynamo. It has had one for at least 4 billion years. The dynamo is what makes a compass needle point north. It is what guides migrating birds across continents. It is what causes the auroras in the polar skies. But more importantly, the dynamo is what generates the magnetic field that surrounds Earth. And that field is one of the most important features any rocky planet can have. Because here's what the field does. Out in space, the sun is constantly sending a stream of charged particles in every direction. We call this stream the solar wind. It is fast, it is energetic, and it is very good at stripping atmospheres away from planets that have no protection. Earth's magnetic field deflects the solar wind. The charged particles hit the field, get pushed sideways around the planet, and slide past us into space without ever reaching the atmosphere. The field is a shield. Without it, the solar wind would slowly chew our atmosphere away, the same way it has chewed away countless other atmospheres in the universe. So a working dynamo, deep inside a rocky planet, is what produces the magnetic shield that protects the surface and the atmosphere from the sun. Mars used to have one, and then it stopped. Now we come to the heart of tonight's story. Why did Mars's dynamo stop? Earth's dynamo is still running. Earth's core is still hot and liquid and churning. Why is Mars's core cold and quiet today? The answer is size. And once you understand why size matters, the rest of tonight's story falls into place. Let me show you with something familiar. Imagine 2 cups of tea, identical temperature, both freshly poured. One is a small espresso cup, holding maybe 100 milliliters. The other is a large mug, holding 500 milliliters. You leave them both on the table. Which one cools down first? The small espresso cup every time, because the small cup has less tea inside, but proportionally more surface area on the outside compared to its volume. The heat inside escapes through the surface. With less interior heat to lose and more surface to lose it through, the small cup chills down within minutes. The big mug stays warm for an hour. This is the same physics that determines how planets cool down. A planet, after it forms, is hot. It loses heat to space through its surface, slowly, over time. The bigger the planet, the more interior heat it has, and the smaller its surface area is in proportion. So bigger planets stay hot longer. Smaller planets cool faster. Mars is small, much smaller than Earth. To give you the numbers, Earth has a diameter of about 12,700 kilometers. Mars has a diameter of about 6,700 kilometers. Mars is roughly half the diameter of Earth. But because volume scales with the cube of size, Mars's total volume is only about 15% of Earth's volume, and Mars's mass is only about 10% of Earth's mass. 10%. Mars is, by weight, 1/10 of our planet. Now apply the espresso cup logic. A planet that is 1/10 the mass of Earth has dramatically less interior heat to begin with, and a proportionally much larger surface to lose that heat through. So Mars cools faster than Earth. Much faster. And here is what that means for the dynamo. The dynamo runs on the temperature difference between the deep core and the upper mantle. Specifically, the dynamo needs the core to be hotter than the rock above it, hot enough that the liquid metal keeps churning and flowing. Once the temperature difference fades, the metal stops moving. Once the metal stops moving, the magnetic field stops being generated. On Earth, the temperature difference is still strong. The deep core is still hotter than the mantle by thousands of degrees. The metal still churns. The dynamo still runs. The field still protects the planet. On Mars, the temperature difference faded much earlier. The core cooled too fast. The metal slowed down. The churning weakened. And eventually, possibly somewhere around 4 billion years ago, the dynamo collapsed. This was not a failure. It was not a flaw. It was just what happens when a small planet sits in space for a long time. Mars was always going to cool faster than Earth, simply because Mars is smaller. The dynamo was always going to run out sooner. The protection was always going to fade. And once the protection faded, everything else became a matter of time. Mars did not just lose its water. It lost the ability to keep its water. And that ability is something a planet only gets if it is born big enough to hold it. The line we held in Part 1 is what we are now starting to see in mechanism. The size of the planet, the depth of the core, the rate of cooling, the lifetime of the dynamo are all linked. And Mars, being small, did not get to keep them. So when did Mars's magnetic field actually collapse? When did the dynamo stop? This is a hard question to answer, because we cannot directly observe events that happened 4 billion years ago. But we have a tool. The tool is called paleomagnetism, and it is one of the most beautiful pieces of geological detective work in modern science. Here is how it works. When molten rock cools and solidifies, the iron-bearing minerals inside it line up with whatever magnetic field is in the environment at the time. Like tiny compass needles, they freeze in position pointing toward the magnetic poles. Once the rock is fully solidified, those tiny aligned minerals stay locked in place, sometimes for billions of years. The rock becomes a permanent record of the magnetic field that existed when it formed. On Earth, this is how we know that Earth's magnetic field has reversed many times throughout history. We can read the orientation of magnetic minerals in rocks of different ages and see the field flipping back and forth across geological time. On Mars, we can do the same kind of reading. We have meteorites from Mars that have landed on Earth. They were blasted off the Martian surface by ancient impacts and traveled through space until they fell to our planet. We can pick them up, take them into laboratories, and read the magnetic record they preserve. In May of 2023, a study published in Science Advances, led by a graduate student at Harvard named Sarah Steele, used this technique to refine our timeline of when Mars's magnetic field was active. The study analyzed Martian meteorites and concluded that Mars had a working magnetic field, generated by an active dynamo, until at least 3.9 billion years ago, possibly later, possibly with the field reversing direction at least once during its lifetime, the same way Earth's field reverses. Older studies, based on different evidence, had suggested the dynamo died earlier, possibly 4 billion years ago or before. Steele's work pushed the date forward, suggesting the field lasted longer than we previously thought. Some other studies have argued the field may have lasted even longer than that, possibly stopping and restarting at least once. So the timeline is not perfectly settled, but the broad picture is consistent. Mars had a dynamo for the first 500 million years of its life or so. The dynamo collapsed somewhere around 3.9 to 4 billion years ago. After that, the protective magnetic field was gone. And the timing matters, because 3.9 billion years ago is right at the end of the warm, wet Noachian period. The collapse of the dynamo is, almost certainly, what triggered the slow loss of Mars's atmosphere. Once the shield was gone, the sun could start doing what it does to any unprotected atmosphere in space. Eat it. That is what we have to talk about next. What the sun actually does to a defenseless planet. Most people, when they think of the sun, think of light and heat. That is mostly correct. The sun does send us light. It does send us heat. But the sun also sends us something else. Something we cannot see, but which is constantly arriving at our planet, every second of every day. For as long as the sun has existed, it is a stream of charged particles, mostly protons and electrons, blowing outward from the sun in every direction at speeds of around 400 kilometers per second, sometimes faster during solar storms, sometimes slower during quiet periods, but always there, always blowing. This stream is called the solar wind. Let me give you a way to picture it. Imagine standing in front of a powerful fan. Not just air coming at you, but air with millions of tiny invisible BBs mixed into it, traveling at high speed. That is roughly what space looks like, near any planet, all the time. The solar wind is the cosmic equivalent of standing in that fan, constantly being hit by particles you cannot see. On Earth, our magnetic field deflects the solar wind. The charged particles hit the field, get pushed sideways, and stream past the planet without reaching the atmosphere. Some particles do leak through, near the magnetic poles, and they cause the auroras we see in the northern and southern skies. But the bulk of the solar wind never touches our atmosphere. Earth's shield holds. On Mars, after the dynamo died, there was no shield. The solar wind started reaching the upper atmosphere directly. And once it did, three things began to happen. All three are still happening today, 4 billion years later. The first thing is called sputtering. When a high-speed particle from the solar wind hits an atom in the upper atmosphere, it can knock that atom hard enough to send it flying off into space, like a billiard ball hitting another billiard ball. The atmosphere atom, kicked by the incoming particle, gets enough energy to escape Mars's gravity and never come back. The atmosphere loses one atom at a time, billion after billion, year after year. The second thing is called ion pickup. Some atoms in the upper atmosphere, when they get hit by ultraviolet light or solar particles, lose an electron and become positively charged. We call these ions. Once an atom is an ion, it feels electric and magnetic forces in a way a neutral atom does not. The solar wind, which carries its own magnetic field, picks up these ions and accelerates them away. The atmosphere loses another batch of atoms this way, every second, every day. The third thing is called photochemical escape. Some atmospheric molecules, when they are hit by ultraviolet light, break apart. The fragments sometimes have enough energy to escape the planet's gravity even without being kicked by the solar wind. They simply fly off on their own. All three processes work together, all the time. The solar wind, the ultraviolet light, the chemistry of the upper atmosphere, all conspiring to thin the air, slowly, persistently, over billions of years. Mars has been losing its atmosphere this way ever since the dynamo died. And we know this not because we're guessing. We have a spacecraft in orbit around Mars, right now, measuring the loss in real time. Its name is MAVEN. MAVEN is short for Mars Atmosphere and Volatile Evolution. It was launched in November of 2013 from Cape Canaveral and arrived at Mars in September of 2014. Its mission, as the name suggests, is to study how Mars loses its atmosphere, to measure the rates, to watch the processes happen, to turn the speculation about Mars's atmospheric history into a measured set of numbers. For more than 11 years, MAVEN orbited Mars and built up the most detailed picture of the Martian atmosphere we have ever had. In December of 2025, after over a decade of continuous operation, the spacecraft suddenly went quiet. NASA lost contact with MAVEN on December 6, 2025, when the spacecraft emerged from behind Mars during a routine communications blackout and never re-established its signal with Earth. Recovery efforts continued through early 2026, but as of this recording, contact has not been restored. A NASA Anomaly Review Board has been convened to assess what likely happened and whether the spacecraft can be recovered. Whether or not MAVEN ever speaks to Earth again, the 11 years of data it sent back are now part of the permanent record of what we know about Mars. The headline finding is this: Mars is losing its atmosphere at a rate of about 2.5 kilograms per second. That is the total. All processes combined, sputtering, ion pickup, photochemical escape, all rolled into one number. About 2.5 kilograms of atmospheric gas every second, leaving Mars and never coming back. 2.5 kilograms per second. That sounds small. On a human time scale, it is small. 2.5 kilograms is the weight of a small bag of flour, but the number compounds. Every minute, Mars loses 150 kilograms. Every hour, 9,000 kilograms. Every day, more than 200,000 kilograms. Every year, around 79,000 metric tons of atmosphere drift off Mars and into the empty space of the inner solar system. And this has been happening. more or less continuously, since the dynamo died. For billion years of atmospheric loss, the math gets large. By any reasonable calculation, Mars has lost the majority of its original atmosphere this way. Estimates vary, but most modeling suggests Mars's atmospheric pressure today is less than 1% of what it was during the Noachian. The original thicker air, the kind of atmosphere that supported rivers and lakes, is almost entirely gone, scattered through interplanetary space as individual atoms over billions of years. Maven also measured something else important. The losses are not constant. They depend on the activity of the sun. When the sun is more active, with stronger flares and a denser solar wind, Mars loses atmosphere faster. During solar storms, the rate can spike to many times the normal level. The young sun, 4 billion years ago, was more active than the modern sun. Solar flares were more frequent. The solar wind was denser. So the rate of atmospheric loss in the early days, just after the dynamo collapsed, was probably higher than what we see today. The loss happened fast at first, then slowed, then settled into the slow, steady erosion we measure now. So the picture today is of a planet that has been steadily losing its air for 4 billion years, with a measurable, ongoing process that we can watch happen in real time from orbit. Maven was not just confirming a theory. It was watching the slow death of an atmosphere as it continued to play out. And in December of 2022, 3 years before its silence, Maven observed something unusual, something dramatic, something that, while it did not kill Mars, did show, in vivid detail, just how sensitive the planet is to the solar wind it can no longer defend against. On December 25, 2022, Maven encountered something it had never measured before. The solar wind, the constant stream of charged particles blowing past Mars, suddenly dropped to almost nothing. The density of solar plasma, which is normally a few particles per cubic centimeter, fell to 1/10 of that. A void in the wind, a gap in the cosmic breath that has been blowing past Mars for 4.5 billion years. The cause was a special kind of solar event. A few days earlier on the Sun, a fast-moving stream of particles had pushed ahead of itself, sweeping out a region of nearly empty space behind it. By the time the void reached Earth on December 25th and reached Mars on December 26th, the solar wind in that region was almost gone. Not for long, just for a couple of days, but long enough for spacecraft to measure. And what Maven measured, when the wind disappeared, was striking. The Martian atmosphere, no longer being pressed against by the solar wind, expanded outward, dramatically. The bow shock, the boundary where the solar wind normally hits Mars's environment, ballooned by thousands of kilometers. The magnetosphere, the weak-induced field around Mars, swelled. The terminator region of the planet, where day meets night in the upper atmosphere, transitioned from a magnetized state to an unmagnetized state. Then, 2 days later, when the solar wind returned to normal density, everything snapped back. The atmosphere compressed. The boundaries returned to their usual positions. Maven, which had been temporarily floating in a place where no spacecraft had been before, found itself back in the regular structure of the Martian space environment. Now I want to be careful here. I want to make sure I am not making a claim the data does not support. The disappearing solar wind event in December 2022 is not what killed Mars. It was a brief, 2-day, naturally occurring fluctuation. Mars survived it just fine. The atmosphere returned to its usual state within hours of the wind coming back. The event did not, by itself, accelerate the long-term loss of Martian atmosphere in any meaningful way. But the event is important for a different reason. It is a demonstration. It shows, in vivid detail, just how sensitive Mars is to the solar wind. When the wind decreases, the Martian environment expands. When the wind increases, the environment contracts. Mars, without its own protective magnetic field, is at the mercy of whatever the sun decides to send. It is a planet whose entire upper atmosphere is constantly being shaped, second by second, by the conditions in interplanetary space. Earth is not like this. Earth has its own magnetic field. The field defines the boundaries. The solar wind can fluctuate, can vanish, can spike, and Earth's magnetosphere remains roughly stable, because it is anchored in the planet's own dynamo. Earth's protection is internal. Mars's protection today is whatever the sun is or is not doing in any given moment. And the December 2022 event, brief as it was, is the kind of thing we will see more of as we get better at measuring Mars in detail. The lesson is not that Mars is dying right now from solar windstorms. The lesson is that Mars, having lost its dynamo billions of years ago, is permanently exposed. The atmospheric loss we see today, 2.5 kilograms per second, would be much higher during the early period after the dynamo died, when the sun was younger and more active. By now, after 4 billion years, what is left of the Martian atmosphere is the thin remainder of what used to be a much fuller envelope. So Mars is sensitive, Mars is exposed, and Mars, today, has only about 1% of the atmospheric pressure it had during the warm, wet Noachian. Where did the other 99% of the atmosphere go? Where did the water go? That is what we have to figure out next. During the Noachian, Mars had a lot of water on its surface, maybe enough to fill a global ocean covering the planet to a depth of hundreds of meters, maybe enough, by some estimates, to cover Mars in a layer of water several kilometers deep, if you had spread it all evenly across the surface. Most of that water is gone today. The surface of Mars, when we measure its atmospheric humidity, is one of the driest places we have ever observed. The polar ice caps still hold significant amounts of water ice, but only a small fraction of what the planet must have started with. Where did the rest of it go? The answer, based on 100 years of measurements and modeling, is that the water of ancient Mars went one of 3 places. Some of it went to space. The same processes that strip atmosphere also strip water. When water vapor in the upper atmosphere is hit by ultraviolet light, it breaks apart into hydrogen and oxygen. Hydrogen is the lightest element. It is so light that it escapes a planet's gravity easily, especially a planet with weak gravity like Mars. Once the hydrogen is gone, it cannot be recombined into water. The oxygen, heavier, sometimes stays behind, sometimes also escapes. But the hydrogen leaves first, and once it leaves, the water that hydrogen used to be part of is permanently broken. MAVEN has measured this process directly. It has watched hydrogen escaping from the upper atmosphere of Mars in real time. The escape rate varies. It is higher when Mars is closer to the Sun in its orbit, lower when Mars is farther. But the cumulative loss, over 4 billion years, has been enormous. Estimates suggest that Mars has lost the equivalent of an entire global ocean's worth of water this way. Maybe more than one ocean. Hydrogen, atom by atom, drifting off the top of the atmosphere into the empty space between worlds. Some of the water went into the sky. Mars has thin clouds today, mostly very high altitude, mostly water ice. The polar ice caps lock up some of the water in solid form. There's dust mixed with ice across many regions of the planet, and that dust holds onto small amounts of water that come and go with seasons. The visible water reserves of Mars, the ones we can see from orbit or from a rover, are real. They are a fraction of the original, but they are still there, and some of the water went into the crust. This is the third fate, and for a long time it was the most uncertain. Did Mars's water actually all escape to space, or did some of it sink down into the rock, get absorbed by minerals, and stay there, hidden, for billions of years? Until very recently, we did not have a good way to answer this question. The Mars rovers can only drill a few centimeters into the surface. The orbiters can see the top layer of dust and rock. But what is happening kilometers below the surface, in the deep crust, was effectively invisible. We were guessing. Then, in 2024, a piece of evidence arrived that changed the picture. The evidence came from a spacecraft called InSight, which had been silently sitting on Mars for 4 years. And the discovery it made, after the mission had officially ended, may turn out to be one of the most important things we have ever learned about the Red Planet. InSight was a Mars lander, launched in May of 2018, that landed on the Martian surface in November of the same year. It touched down in a flat plain called Elysium Planitia, near the equator. Its mission was different from the rovers that had come before. InSight did not move. It sat in one place for the entire mission. And what it did, instead of driving around, was listen. InSight carried a seismometer. A seismometer is a device that measures vibrations passing through the ground. On Earth, we use seismometers to detect earthquakes. The waves from an earthquake travel through the planet, and emerge at the surface in patterns that depend on what is between the source of the quake and the seismometer. By measuring the patterns, we can figure out the structure of the planet's interior, even though we cannot directly see it. InSight's job was to do the same thing for Mars, to listen for Mars quakes, to use the vibrations from those quakes to figure out what is inside Mars, layer by layer, from the surface down to the core. The mission lasted 4 years, until December 2022, when dust accumulating on the solar panels finally made it impossible to keep the spacecraft alive. By then, InSight had recorded over 1,300 Marsquakes, a 4-year archive of seismic data from a planet we have never been able to explore from inside before. That data, after the mission ended, kept being analyzed, and in August of 2024, a team led by a researcher named Noachian, right at the Scripps Institution of Oceanography in California, working with colleagues at UC Berkeley and elsewhere, published a paper in the Proceedings of the National Academy of Sciences. The paper used the seismic velocities measured by InSight to look at the deep structure of the Martian crust beneath the lander. And what the team found when they ran the rock physics models was striking. Between 11.5 kilometers and 20 kilometers below the Martian surface, the rock matched the kind of seismic signature you would get if it were saturated with liquid water. Not ice. Liquid. Trapped in fractured igneous rocks, sitting in the pores between the cracks, kept warm enough at depth that it has not frozen solid. The team estimated, if their finding is representative of Mars in general, that the total amount of water in this mid-crust layer would be enough to cover the entire planet to a depth of 1 to 2 kilometers, more than the volume people had hypothesized for the ancient Martian oceans, hidden in the rock the whole time. Now I want to be careful about how I describe this. The data does not prove definitively that the mid-crust layer contains water. There are alternative explanations. The seismic signature could potentially be produced by other materials, like air-filled fractures or certain mineral mixtures. A follow-up study in late 2024 even argued that liquid water might not be the only answer the data supports. The interpretation is still being debated by the scientific community, but the most likely explanation, based on the current evidence, is liquid water. Possibly a lot of it, possibly more than the surface ever held during the Noachian, just sitting there, in the deep crust, kilometers below where any rover can reach. If the finding holds up, it changes how we think about Mars's water history. The story is no longer that Mars's water all escaped to space. The story becomes that some of it escaped, and some of it sank. The crust acted like a sponge, slowly absorbing the water that the surface was losing as the climate cooled and the pressure dropped. Over time, the surface dried out, but the water, much of it, did not leave the planet. It just left the surface. And the implications for biology, if you want to think about that, are significant. Cold subsurface water is exactly the kind of environment where Earth's deepest microbes live. We have found microbes in deep mines, in oil wells, in groundwater systems kilometers below ground. If Martian biology ever existed, the deep crust may be exactly where it would have retreated when the surface became uninhabitable. Whether anything is alive down there now, we have no way to know. But the conditions, possibly, are still there. So Mars is not as dry as it looks. The cold red desert at the surface is, in a sense, only the visible layer of a much wetter underground world. The water did not all leave. Most of it just hid. But here is the question this raises. Why did the water leave the surface in the first place? Why did Mars stop being able to hold its rivers and lakes? And the answer, the deepest answer, the one we have been building toward all along, is finally ready to be said. Now I want to bring everything together, because the title of this video promised the real reason, and I want to give it to you cleanly, in one sentence, before we widen out again. The real reason Mars turned from a living world into a dead planet is this. Mars was born too small to keep its engine running. That is the whole answer. The whole chain. One sentence. Let me explain what I mean by that, because it holds the whole case together. The water did not just leave Mars. The atmosphere did not just leave Mars. The magnetic field did not just leave Mars. None of these things happened in isolation. They are consequences. They are downstream effects. The deeper cause, the cause that made all the other losses inevitable, is upstream of all of them. The deeper cause is the size of the planet at the moment it was born. Here is the chain, in one piece, the way the planet actually lived it. Mars formed about 4.5 billion years ago, with about 10% of Earth's mass. Because it was small, Mars's interior cooled quickly. The hot metal core, which when Mars was young was molten and churning and generating a magnetic field, began to lose its temperature gradient much earlier than Earth's core did. The dynamo weakened. Around 3.9 billion years ago, the dynamo collapsed. The magnetic field shut off. Once the field was gone, the protective shield around the planet was gone. The solar wind, which had been deflected for the previous 500 million years, started reaching the upper atmosphere directly. Sputtering began. Ion pickup began. Photochemical escape began. The atmosphere started to thin. As the atmosphere thinned, the surface temperature dropped. With less air to trap heat, more heat radiated to space. The water cycle weakened. Rivers ran less. Lakes froze and did not melt. Some water escaped to space as hydrogen. Some sank into the crust. The surface dried out. And here is the key fact. Once that change started, it could not stop. Each loss made the next loss easier. Less atmosphere meant less protection, meant more loss. Less water meant less cycling, meant less. Weather meant less mixing of the atmosphere, meant more loss. The planet became locked into a one-way slide. Toward thinner. Toward drier. Toward colder. Toward the cold red desert it is today. And every step in that chain was, ultimately, set in motion by Mars's size. If Mars had been bigger, the core would have cooled slower. The dynamo would have lasted longer. The magnetic field would have held. The atmosphere would have stayed. The water would have stayed. The chain would not have started. This is what I mean when I say Mars died because it was too small. Not too small in the sense of being a failed planet. Mars is a perfectly successful rocky planet. It exists. It orbits. It has its own geology and its own complex history. But Mars was too small to keep its protective machinery running for the full age of the solar system. The machinery was always going to give out before our sun finished its main lifetime. And once the machinery gave out, the rest was inevitable. Earth, being bigger, kept the machinery. Our core is still hot. Our dynamo is still running. Our magnetic field is still up. Our atmosphere is still here. Our water is still on the surface. We are still warm. We are still wet. We are still the kind of planet where a creature can sit in a chair and listen to a video about another planet that did not get to keep all of these things. Mars did not just lose its water. It lost the ability to keep its water. And that ability is something a planet only gets if it is born big enough to hold it. That is the real reason. Mass is destiny. The size you are born with sets the lifetime of your inner heat. The lifetime of your inner heat sets the lifetime of your magnetic field. The lifetime of your magnetic field sets the lifetime of your atmosphere. The lifetime of your atmosphere sets the lifetime of your water. And the lifetime of your water sets the lifetime of any chance for life to take hold and stay. Mars was born with the wrong number. The number was its mass. Everything else followed. Now I want to flip the picture. Because tonight has been about Mars, but the story is also about Earth. About why we are here, sitting on a planet with rivers and oceans and a thick blue sky, while our smaller neighbor sits cold and red and quiet just one orbit out from us. Earth is bigger. That is the first answer. Earth has about 10 times the mass of Mars. Earth has more interior heat, more deep rock, more protected core volume, more time before the dynamo runs out. The size advantage we have over Mars is not small. It is the difference between a planet whose engine runs for billions of years and a planet whose engine runs for a few hundred million. But size is not the only thing Earth is going for it. Several other factors line up to keep our planet warm and wet, and it is worth walking through them, because they show how narrow the window for habitability really is. The first factor is distance. Earth orbits the Sun at about 150 million kilometers. Mars orbits at about 228 million kilometers. Earth gets, on average, about 40% more sunlight than Mars does. So even if Mars had kept all its atmosphere, the surface would still be colder than Earth's, simply because the Sun is fainter from there. The second factor is the Moon. Earth has a large moon, formed when a Mars-sized body slammed into the early Earth and threw up a ring of debris that eventually coalesced into our familiar lunar companion. The moon has done something subtle but important for Earth's habitability. It stabilizes our axis. The angle at which Earth tilts toward the sun stays roughly constant, which means our seasons stay roughly predictable, which means our climate stays roughly stable over long periods. Mars does not have a large moon. Mars has two small moons, Phobos and Deimos, but neither is big enough to stabilize the planet's axis. As a result, Mars's axial tilt has wandered dramatically over its history. Sometimes Mars is tilted at about 25 degrees, similar to Earth. Sometimes it has tilted to over 45 degrees, which would cause extreme climate swings. The instability of Mars's tilt is part of what made the planet hard to keep warm for long periods, even when it had its atmosphere. The third factor is plate tectonics. Earth's crust is broken up into large pieces, called plates, that slowly slide around on top of the hotter mantle below. The motion of these plates does something important. It cycles material between the crust and the deep interior. Carbon dioxide that gets trapped in rocks at the surface eventually gets carried back down into the mantle, melted, and released back into the atmosphere through volcanoes. This carbon cycle, called the carbonate-silicate cycle, acts as a natural thermostat for Earth's climate. When the planet gets too cold, less carbon dioxide gets locked into rocks, more stays in the atmosphere, and the greenhouse effect warms things up. When the planet gets too warm, more carbon dioxide gets locked into rocks, less stays in the atmosphere, and the planet cools. Mars probably never had plate tectonics, or if it did, the tectonics shut down very early. The Martian crust is mostly one solid piece. The carbon cycle that Earth runs to keep its climate stable was never really running on Mars. So even if Mars had kept its atmosphere, it would not have had the climate-stabilizing system that Earth uses to stay habitable across long stretches of geological time. So Earth has size, distance, a stabilizing moon, and plate tectonics. Mars had small size, weaker sunlight, an unstable tilt, and probably no working tectonic cycle. Even before the dynamo collapsed, Mars was operating with a much narrower set of advantages. Once the dynamo went, the narrow window was too narrow to hold. This is what I find quietly humbling about our situation. We are not on Earth because Earth is the obvious place for life. We are on Earth because our planet had a particular combination of advantages, all lining up at the right moment, that allowed habitability to persist for billions of years. The combination is rare. It may not be unique in the universe, but it is also not common. The fact that we are alive on a planet that is this lucky is not something to take for granted. It is something to notice. Before we close, I want to address one more thing, because if you have been listening carefully, you have probably been holding a question in the back of your head all night. The question is, did anything ever actually live on Mars? And the honest answer, today, is that we do not know. We have not found definitive evidence, but we have not ruled it out either. And in the last few years, the evidence has gotten interesting. In July of 2024, the Perseverance rover, drilling in Jezero crater, sampled a rock that was given the nickname Chiava Falls. The rock had unusual features. Specifically, it had structures that, on Earth, are sometimes associated with microbial life. Small spots, called leopard spots, where iron and phosphate minerals are arranged in a pattern that, in Earth rocks, is sometimes produced by ancient bacteria. The chemistry of the rock also showed signs that organic compounds, the carbon-based molecules life is built from, may have been present. NASA, when announcing the find, was careful with their language. They called Chiava Falls a potential biosignature. Not proof, not confirmation, just a sample of rock that has features which, in some plausible interpretation, could be the remnants of past biological activity. The team noted that alternative explanations exist. The leopard spots could be produced by non-biological chemical processes. The organic compounds could have arrived from comets or asteroids rather than being made by life. The patterns could be a coincidence of geology rather than a signature of biology. Chiava Falls is now stored in a tube on the surface of Mars, waiting for a future mission that could potentially bring it back to Earth for laboratory analysis. The original NASA ESA Mars sample return mission, which was designed to do exactly that, has run into political and budgetary problems. As of this recording, the mission's future is uncertain. Whether Chiava Falls will ever reach an Earth laboratory, where the question of whether it contains real biosignatures could finally be settled, is itself an open question. In March of 2025, a different team published research on a different rock, one sampled by the older Curiosity rover in Gale Crater years ago. The rock, called Cumberland Mudstone, contained traces of long-chain alkanes, the largest organic molecules ever detected on Mars. These are carbon molecules that, on Earth, are typically produced by life, although they can also be produced by some non-biological chemistry under the right conditions. The new study reanalyzed the chemical patterns and proposed, cautiously, that these molecules could be the degraded remains of an ancient Martian biosphere. Or, alternatively, they could be the products of hydrothermal chemistry that has nothing to do with life. So the question is genuinely open. We have hints. We have potential signatures. We do not have proof. And this is the right place for tonight to land on the biology question. Not with a confident yes, because the evidence does not support that. Not with a confident no, because the evidence does not support that either. With an honest, careful, possibly yes, possibly no shrug, while the rocks sit in their tubes on Mars, waiting for a chance to be examined more carefully. Tonight, in May of 2026, the question of whether Mars ever had life is genuinely unsettled. And it may stay unsettled for many years to come. But the conditions for life were there. The water was there. The atmosphere was there. The time was there. Whether biology used those conditions, we still do not know. What we do know is that the conditions did not last. That is what tonight has been about. Not whether life happened, whether the world that could have supported life kept itself together long enough. And the answer to that question, we now have. The world did not keep itself together. The world died because the engine that sustained it stopped running. And the engine stopped because the planet was too small to keep it going for long enough. Here's one more question that comes up whenever people talk about Mars. Could we bring it back? Could humans, with technology, restart the engine, restore the atmosphere, give the planet back its rivers and lakes? The general name for this idea is terraforming, making a world Earth-like. And I want to be honest about this, because terraforming Mars is one of the most popular ideas in science fiction and one of the least supported by actual physics. The basic idea sounds simple enough. Find a way to thicken Mars's atmosphere. Find a way to warm the surface. Find a way to keep the new atmosphere from being stripped by the solar wind. Find a way to make liquid water possible again. Then, theoretically, the planet could once more support the kind of conditions it had during the Noachian. In practice, every step in that plan runs into problems that are much harder than they first appear. Thickening the atmosphere is the first hurdle. Mars currently has about 1% of Earth's atmospheric pressure. To get back to a Noachian-like environment, you would need to multiply that by something like 100 or more. Where does the gas come from? One proposal is to release the carbon dioxide that is currently locked in Mars's polar ice caps and frozen into the soil. A 2018 study from researchers at the University of Colorado Boulder calculated how much gas could be released this way. The conclusion was that even if you released all of it, you would only get to about 7% of Earth's pressure. Not enough to support liquid water on the surface for any significant time. The carbon dioxide budget Mars currently has is, by orders of magnitude, less than what would be needed to make the surface habitable. Warming the planet is the second hurdle. Mars is much farther from the sun than Earth is. Even with a thicker atmosphere, the surface would be cold by our standards. To compensate, you would need to amplify the greenhouse effect significantly, which means even more atmosphere than the simplest calculation suggests. Some proposals involve injecting greenhouse gases that are much more powerful than carbon dioxide, but the quantities required are still enormous. Keeping the atmosphere is the third hurdle, and it is the one most people forget. Even if you somehow built up a thick Martian atmosphere over a few centuries, the same processes that stripped the original atmosphere would still be operating. The solar wind would still be hitting an unprotected upper atmosphere. The dynamo would still be dead. The magnetic shield would still be missing. Whatever atmosphere you built would slowly start drifting away again, the same way the original one did. There are speculative ideas for solving this. Some researchers have proposed building a massive artificial magnetic field generator near Mars, sitting between the planet and the sun, deflecting the solar wind before it ever reaches the atmosphere. The engineering would be staggering, The energy required would be staggering. The scale would be unlike anything humanity has ever attempted in space. So could Mars be revived? In principle, with enough time and energy and technology, possibly. In practice, with anything resembling current technology, no. The scale of the project is many orders of magnitude beyond what we can do today. And even if we someday could do it, the planet would still be smaller than Earth. The fundamental issue, the size problem we walk through tonight, would still be there. We would be, at best, holding back a tide that the physics of the planet wants to pull back in. Mars, as a habitat for humans on the surface, may always require artificial support, bases under domes, air provided by machines, water harvested from the deep crust or from the polar caps. The idea of Mars as a true second Earth, with open skies and breathable air and oceans, is much further away than most science fiction suggests. And the reason it is further away is the same reason the first Mars died. The planet was born too small. Tonight we walk together through the slow death of a world. The Noachian, when Mars had rivers and lakes and a thicker sky. Jezero crater, where Perseverance is sitting on a dried lake floor, drilling into the rock that water deposited billions of years ago. The 15,000 kilometers of riverbeds in Noachian Terra, preserved as fossilized channels in the red highlands. The dynamo, the deep churning of liquid metal in Mars's core, generating a magnetic field that for 500 million years protected the surface. The collapse, around 3.9 billion years ago, when the dynamo went quiet. The solar wind, reaching the upper atmosphere unopposed for the first time. The slow scouring, 2.5 kilograms per second, year after year, for 4 billion years. The water lost to space, frozen into the polar caps, sunk into the crust where InSight's seismic data found it kilometers below the surface. Chiava Falls, the rock waiting on Mars for a sample return mission that may or may not ever come. The cold red desert that Mars is today. And the real reason, Mars was born too small to keep its engine running. Mass is destiny. The size you are born with sets the lifetime of everything else. Here is what I want you to take with you when you turn this off, or when you wake up halfway through and start the next part. Mars is not just a story about Mars. Mars is a mirror. When we look at Mars, we are looking at what happens to a planet that runs out of internal heat too soon. The thinning of the atmosphere, the freezing of the surface, the slow scouring by solar wind, are not unique to Mars. They are general. They will eventually happen to any rocky planet whose dynamo dies, including, in the very long term, Earth. That is the long-term truth Mars is showing us. Habitability is not permanent. Habitability is a phase. Every rocky planet, big or small, eventually loses the conditions that allow surface life. The big planets just get more time, and we get to be alive during the long phase of Earth's habitability. Not at the end, not at the very beginning, before life had even started. Somewhere in the broad warm middle, when the planet's machinery is still humming, when the field is still strong, when the air is still thick, when the water is still flowing on the surface. We get this window. It is a long window by human standards, but a brief window by cosmic standards. Mars did not just lose its water. It lost the ability to keep its water, and that ability is something a planet only gets if it is born big enough to hold it. We are on the planet that was born big enough. We are alive in the time when its machinery is still working. The next time you take a sip of water, the next time you breathe in air, the next time you feel the wind move past your face on a walk outside, I want you to feel something quiet. The wind, the water, the air are all there because the planet you are standing on is keeping its engine running. The engine has been running for 4.5 billion years. It will keep running for a long time still. But it is running. It is doing work to keep us alive. And every breath you take, every drop of rain that falls, every river that flows, is the proof. Earth is, right now, a living world. Not in the sense that we have to prove biology exists here. Biology is obvious. Earth is a living world in the deeper sense, that the planet itself is alive, with a hot interior and a flowing core and a magnetic shield and a dynamic atmosphere. Mars used to be that kind of world too. Mars is not anymore. And one day, very far in the future, neither will Earth be. The cold red desert that Mars is today is the future every rocky planet eventually walks toward, given enough time. We get to be here for the warm part. We get to see the rivers, while the rivers are still here. That is the gift. Good night from a planet that is still alive. Good night from a place where the engine still runs, where the rivers still flow, where the air still wraps around the world the way it used to wrap around Mars 4 billion years ago, before the long, slow, patient cooling that turned a living world into a dead planet. If you enjoyed tonight, a small subscribe before you go means the next video finds you, and finds others like you who would love it. It is a small thing for you, and a real one for me, and it helps this kind of slow, careful science reach more people who would benefit from it. Good night from here, where the sky is kinder, and the engine still hums.